Alrighty, so I guess we'll call this section 1.4a notes because I highly doubt we're going to finish them today. Like I said, I'm not worried about it. It's not going to be the end of the world. But we are going to cover a couple things that I know the students struggle with. So tomorrow we're going to practice those things after we finish the notes. Like I said, homework won't be due tomorrow. It'll be due the day after. We start with sum, difference, product, and quotient of functions. And this is something that you did in Algebra 2. It literally means you're going to take two functions and add them or subtract them or multiply or divide. The neat thing about functions is when you do arithmetic with two functions, what you end up with is another function. It's actually really neat when you're a nerd like me that's the case, that you can take two functions and do math with them, create something completely new, and the result is always a new function. It's pretty cool. As long as you understand function notation, this will be pretty easy. F plus g of x, that just means add the two functions. F minus g of x just means subtract the functions. Watch this. Order matters. Okay, so if it says f minus g, you have to put f first. If it says g minus f, you have to put g first. Just pay attention to order on that one. Fg of x, that means multiply them. And f over g of x, that means divide. And the only caveat is for division, the bottom is never allowed to equal 0. So as long as and also order matters, watch the order because I could say g over f or I could say f over g. As long as the denominator function never equals 0, you're in good shape. So what that gets us to is finding domain restrictions again. So in 1.2, what I would consider the hardest material of 1.2 was finding the domains of functions, right? That was the stuff that we all had questions about. It's going to happen again. So we get to practice those skills from 1.2 when we build our new functions. We have to find f plus g, f minus g, f times g, f over g, and then gg for good measure. No gamers in the room? GG? Good game. Anyway, we have to find the domain of each of these. Okay, well, f plus g, you just say x squared plus square root of x plus 1. Done. I mean, there's no reason to break your brain. There it is. They're not like terms. You can't do any other math. Domain for this one. Well, x squared is all real numbers, so you don't have to worry about that. Really, the only thing that's going to matter is the radical, right? Underneath the radical must not be negative. That means that the smallest x you can put in there is -1. If you're not sure how we do it, just recap. You go, okay, x plus 1 has to be greater than or equal to 0. Subtracting 1 from both sides gives us that x is greater than or equal to -1. So as an interval, -1 to positive infinity is the domain of our new function. And it's going to be the exact same domain of f minus g because, again, x squared is everything. The only difference is we're going to have a minus sign in front of a radical now. Same domain. Of course, the functions would look different if you were graphing them. Luckily, you're not. I don't even know what that would look like, to be honest with you. No clue. I do know that it would have a restricted domain, though. F times g is legitimately just put the x squared in front of the radical. And again, x squared has no restrictions, so the domain is -1 to infinity, bless you. This stuff, I'm gonna be honest, this stuff's kind of boring. Stuff down below is more fun for me. F over g. Okay, finally, something a little bit interesting. F over g of x. X squared over square root of x plus 1. This one does not have the same domain. And the reason why is because if you use that -1 that I put that bracket on, the bottom equals 0. That's not allowed. So it's nearly the same domain, Nearly the same. Well, now what you do is you just put a parenthesis on the -1. This way the bottom can never equal 0, because now you can't plug in -1. And I kind of ran out of vertical space, so I'm going to have to go over there and squeeze it in that white area I have for GG. And GG was done on purpose. So Max says the result is going to be x plus 1. And the reason why he says that is because that squared the radical, right? So let me go ahead and write that. I'm going to show the work, of course. So GG of x is root x plus 1 times root x plus 1. Oops, sorry. That looks like alpha. When I write real fast, the board doesn't know that I picked the pen up. X plus 1, which has a net result of x plus 1, right? So what is its domain? That's the real question. What's the domain?
-1. Anything.
McKinley, what are you trying to say?
It's all real numbers.
She says all real numbers. And I'm trying to remember. Crap, I just forgot your name. I'm sorry. What's your name? Brooks. You know what? I was afraid I was wrong. I was thinking that, but I didn't want to be wrong. Brooks, what do you think? Do you agree with McKinley? Is it all real numbers? So Brooks disagrees. He thinks it's the -1 to infinity with a bracket. So what I would be interested in knowing is what everybody thinks, because we have two options. Really, those are the two options. It's either all real numbers, or it's the restricted red domain, -1 to infinity, including -1. So I would just be looking for a show of hands, okay? Just a show of hands. If you think it's all real numbers, please raise your hand. Okay. Little bit less than half, and people at home, I'm expecting hands to be seen. I saw yours, McKinley. And now, so does that mean everybody else thinks it's the restricted -1 to infinity? Hands up for -1 to infinity. Okay. Wow, that was weird. It was like legitimately half and half. Neat. Anyway, moving on.
Wait, what's the answer?
Oh, that's right. You want to know? Okay, yeah. It's it's the restricted domain. It is -1 to infinity. The reason why is because you knew that this was the function, regardless of what it simplified to. That is the function. So even though it cleans up to a straight line, if you graph this on a graphing calculator, that straight line begins at -1 and heads towards infinity. So regardless of the simplification, the original functions determined the domain. Neat, huh? I mean, I think that's neat. And that's why GG was asked to be done, because it cleaned up to something that doesn't have domain restrictions. You've seen this happen before. Maybe not to that extreme, but you have seen this happen before. Rational functions. You know, where you factor the top and you factor the bottom and then you cross something off. Well, even though you cross that thing off, it still has a hole in the graph there, doesn't it? So you have seen a simplification where the domain is still being affected by the no-no. Same thing happened here. I think that's pretty neat. That's why I really enjoy this stuff down below. Now, when you were in Algebra 1, I think, well, you should have done it in Algebra 2, you did compositions of functions. Meaning you plugged a function into another function. So you should have done f of g of x before. You should have done g of f of x. This shouldn't be a new concept. It's not, right?
Fog.
Yeah, fog, F-O-G.
It always looks like that to me.
Fog x, yeah, f of g of x or fog x, and of course g of f of x. So compositions of functions is also a really neat idea. Not only can you do arithmetic with functions and get a function, you can substitute a function into another function, and again, the result is a function. Now, when you have learned a boatload of mathematics like me, and you see outside of the numbers and the letters and all that stuff, this is actually a really neat thing. It's something called a space. this kind of mathematics. And this space is closed under certain operations, which is really neat. It means that no matter what kind of things you do inside this space, the result will always be inside this space. And that's neat for mathematicians. So plugging a function into another function results in a function, but it will have really strange domain issues sometimes. You probably didn't see that happening in Algebra 2, but you'll see it now. So what do we have? We have x squared minus 1. Well, that domain, this one's domain is all real numbers, right? That's easy. And then we're going to have square root x. That one's domain is not all real numbers. That one's domain is 0 to infinity, including 0. And composing these things is going to create interesting domains. Square root of a negative number is, yes, is complex, is I. All right, G of F, just like just like division and subtraction, order matters. So whatever's after the O, or whatever is inside the big parentheses, that's what you're plugging in. So if it says G of F, and I'll show this work. Let me get myself some more space. Anyway, for A, and I don't really use fog and goff. I really do prefer this method because it allows me to change the color. This is what I do for Algebra 2, and it shows them, oh, okay, I'm going to plug f of x into g of x. So then I can color code it, where g was the blue stuff and f was the red stuff. So there's our new function, the square root of x squared minus 1. And that can be factored. And that's important, that this factors. Because remember, the domain of any radical is the underneath the radical stuff must be greater than or equal to 0. So what that gives us is this statement. X squared minus 1 is greater than or equal to 0. And this is a quadratic inequality. They come up a lot. So this is going to be those times where we factor it and make a sign diagram and figure out where that quadratic is positive and or 0. This is a difference of two squares, so it instantly factors to x plus 1 times x minus 1, which has two critical values. Well, all you have to do is, so the radical is not gone, but as long as what's underneath the radical is positive, you're in good shape. So I just took the stuff that's underneath the radical so I can factor it and figure out what's going to keep that positive, or 0. We need two critical values on our sign diagram. 2 times where underneath the radical equals 0. One of those is -1, one of those is +1. Picture not drawn to scale because who cares? And you just test your zones. So let's plug in a number, and when I say plug in, I mean drop it in these parentheses just to see. Let's plug in a number smaller than -1, like -2. If I plug in -2 here, I get a negative number, and here I get another negative number. And when I multiply those two negative numbers, I'm going to get a positive result. Something really easy that you can plug in that's between -1 and +1 is Zippo, 0. So when we plug 0 in, we get a positive here and a negative here. And when you multiply a positive and a negative, you get a negative. And lastly, a number bigger than 1, like 2. Plug in a 2 here, it's positive. Plug in a 2 here, it's positive. You have a positive result. So the domain, back to over here, the domain of g of f of x, that's a lot of ofs, is going to be the result of that sign diagram way over there. Wherever it is positive, that's your domain. Well, positive or 0. So our domain is from -infinity up to and including -1. Then there's a gap in our domain, and it picks up again, including 1, and heads off to infinity. Like that. And that's why we practiced that stuff in 1.2. We were getting ready for this. Now on my test, well, I'm going to be honest with you. I'm making a chapter 1 test today with Ms. Klein. on my old test, the one that I can't give you guys because I can't have it out in the wild, it's not that I don't trust my people at home, it's just that that would be kind of naive, right? So we're making all new tests, but on the test I used to give, and then I'll probably give again next year if we don't have remote learning. See if you can cross my fingers. I had actually a pretty tough question. So rather than have questions where I go, hey, what's the domain of this function? And have a question where I go, hey, compose this function. What's its domain? I just go, compose this function, what's its domain? Because it hits the skills completely for me. And it didn't go very well. It's a tough question. This is one of the things we'll be practicing tomorrow. Composing means you're plugging one into the other one, and then we have to find the domain. So hopefully I can find questions like that in the test gen. Yes, sir.
This is kind of unrelated to this.
Oh, okay.
So I know how to find the domain of a function.
Now let's do part B. Composing in the other order. This time we're going to take G and we're going to plug it into F. So let's say we have F of, so my two functions will switch colors now, G of X. So G of X is the square root of X. So I didn't use parentheses on the first one because the only thing that was going to be under the radical was x squared minus 1. But typically when I substitute in, I use parentheses. And this is going to be one of those times where we really need to do it. So we have this situation. This is what F looks like when it's ready to have something plugged into it. And what we're going to plug in is square root of X. You see, you decide what the domain is before you clean it up. Now, in the last little section up above, we had a result of X minus 1, but, or plus 1 or something like that. But the point is, the domain was not all real numbers because the domain is determined before you simplify. So this is where you figure out what your domain is. And the thing that's creating the domain issues is the square root bar. Whatever's underneath the radical must be positive or 0. So your domain for this one is actually pretty easy to see. It's just, oh, the thing under the radical must be greater than or equal to 0. So as an interval notation, you say bracket 0 to positive infinity. It does clean up, though, to x minus 1. So again, you have a straight line that has a beginning and then shoots off to infinity in one direction instead of both. This is one of the skills that we'll be practicing tomorrow, composing and then simplifying and finding domain. Cool beans? We good? All right. What else we have? Can I clear this without anybody freaking out? No spaz? All right, cool. I didn't mean to press that button. Come on, panel, catch up. I meant to press this button. There. Now, for each one of these, we are decomposing. Isn't that fun? We're taking them apart. We've been told for each one of these h of x's that we have, figure out what f and g could have been. Not had to be, because there's lots of answers. Could have been in order for you to decompose, take these apart. So here's how you do this. You ask yourself, what looks like it was a substitution? And that'll be what's on the inside. And it says f of g of x. So g of x is whatever looks like it was substituted. So for part A, what looks like it was a substitution?
Both x plus 1.
Yeah, x plus 1, because it was in two different places. It looks like a substitution. It even looks the way that I did it in the last example with parentheses. So and by the way, this is not the only answer. It's just the easy one. X plus 1 looks like it was.
Easy's good.
Yeah, easy's good, right? Thinking smarter, not harder. It looks like x plus 1 was plugged into x squared minus 3x plus 4. And that's it. That's all we had to do. what I did was, so the question was, where did I get f of x? What I did was I imagined what was being plugged into right here. So there should have been an x there, and we were dropping an x plus 1 into its place. So you're trying to imagine two functions. One of them has something else plugged into it.
Oh, so you just plug an X in wherever there's parentheses?
Yeah, so wherever I saw a set of parentheses, I imagined that those are parentheses because something was substituted into there. So originally there would have been an x that was waiting for substitutions. That's how we do it. And don't worry, this will also be one of the things we practice tomorrow. For B, so again, lots of ways to do it, but there's definitely an easy way. And I think the easiest way is call, just like I did for this first one, for part A, f of x should be the overarching structure of what you're looking at. So for the first one, it looked like a standard quadratic to me. For the second one, what would we say is its overall structure? Square root. I would say that also. So I would say, yeah, the overall structure, which is going to be my f of x, is simply the square root of x. And if we do that, then what did we plug into square root of x is whatever replaced the x.
X cubed plus 1.
Yeah, x cubed plus 1. So yeah, that's all you have to do. Again, there's more than one way. This is just, I think, the easiest way. For example, if you don't mind, can I show you another one? Another way of doing that question? Okay. Alternate way. And it doesn't matter which way you choose. We could have said that the overall structure, which I'm saying is f of x, was the square root of x plus 1. And if we do that, we're going to say that our x was replaced with a x cubed. That gives you the same result. If you plug in x cubed into the square root of x plus 1, you get the square root of x cubed plus 1. Yes, ma'am? So the question was, why couldn't f of x be x cubed plus 1? Because of this, which is why I prefer this notation. You see how g of x is inside the parentheses? That means that g of x had to be the inside stuff. So f of x couldn't be x cubed plus 1 because that would have implied that you were plugging f into g. But this notation says you're plugging g into f. Yes, so if it said g of f of x, the answers just would have been switched, yes. So we want to pay it, and that's why I prefer that notation, because it really tells you which one's getting plugged in. So the inside, imagine the inside of these parentheses is the inside of this structure. Inside is inside. Okay. And question in the back?
So would both of them be correct answers?
Yes, they're both equally correct. Now on a test, remember we test online, so it'll be a multiple choice or a multiple select or something like that. There wouldn't be, I wouldn't try to trick you like that. It would be more obvious. It would probably be like, which one of these is a valid decomposition? And you would just look through it and be like, all right, which one works? And then that would be a time where you have to really pay attention to the order of the structure. Okay, hold on, McKinley. Yes, Max?
You won't do that thing where you like have two that look very similar, but like you won't do that thing where it's like this is a valid option, but this one also seems like a valid option, and then one of them's correct, right? Because some teachers will do that.
It would be, I would imagine this question, because like I said, we're going to make this test today. I would imagine this question would be, which of these is a valid decomposition? And Lily asked, couldn't we say f of x was x cubed plus 1? I'm going to be honest with you, switching them would be one of the wrong answers. So you'd have to pay attention to the order of the structure. Max, what's up?
Yeah, they used h of x and then maybe used f of x and g of x. Why would they do that?
Well, they used h of x because once you compose the two functions, you have a new function, so it just needs its own name. So h, literally the h is just a letter they pulled out of the air. They could have called it P of X or K of X or whatever. And nobody freak out. We will practice this tomorrow, okay? We will practice decomposing tomorrow. Even though the homework is not due tomorrow, I strongly suggest you try to do the homework tonight. That way, if you have questions, you'll know what you need to ask tomorrow. Okay, time to model with composition. In the medical procedure angioplasty, doctors insert a catheter into a heart vein and inflate a small spherical balloon on the tip of the catheter. Suppose the balloon is inflated at a constant rate of 44 cubic millimeters, I almost said cubic meters, holy cow, 44 cubic millimeters per second. First we have to find the volume after an unknown amount of time, and then we say, oh, well, when the volume is capital V, what's the radius, R? And this says write an equation. And then we have to use the equation to solve some stuff. Okay. Well, you're told that the balloon is inflating at a constant rate, 44 cubic millimeters per second. So if you want to know the volume after t seconds, like if it's been 2 seconds, what would you do? If it's been yeah, you would just multiply the 44 by 2, which happens to be the t value. So A is legitimate. Ooh, it's red. I don't like it. A is just our volume is 44 times however long it's been inflating. There it is. Volume is 44t. I'm a bad mathematician. Instead of v, it should say v of t because it is a function in terms of time. There we go. V of t. I forgot we were doing composition, so we need to have the of t part. The next question asks about the radius. So in order to pull off part B, we need to know something about volume of a sphere. Anybody know the equation for the volume of a sphere by heart? Brooks, maybe? That's pi r cubed is part of it. 4/3. That's the whole thing. 4/3 pi r cubed. So the volume of a sphere is 4/3 pi r cubed. And someone said 4/3. Is that meaning you don't remember the 4/3, or just why 4/3? Is that the question? Why 4/3? If you can remember that question at the end of the year, when I've taught you some calculus, I can prove to you that it's 4/3 pi r cubed.
I'm gonna write it down.
You write it down. It's found using calculus. This is the volume of a sphere in terms of R. What did we have to do? It says what is R. When it says what is R, what that means is solve for R. Give me an equation that says R equals. Go fine. Time for us to get R by itself. First and foremost, we're going to want to cancel that fraction. Do you guys know how to cancel fractions?
Multiply it by the opposite.
Not opposite reciprocal, just reciprocal. Multiply by reciprocal. Did I do that in my notes? Something similar to that, yeah. So what we're going to do is we're going to multiply both sides by 3/4. That is going to give us 3v over 4 on the left side. Now on the right side, the fractions have canceled each other, leaving us with pi r cubed. We are still trying to get r by itself. That means that pi can't stay there. Typically, you would just say divide by pi, right? But there's already a fraction over there. So instead of saying divide by pi, let's say something that's exactly the same thing, but it'll make the math easier. Let's say multiply by its reciprocal, 1 over pi. Because when you multiply fractions, you just multiply across the bottom and across the top. So on the left side, I'm multiplying 3v to that 1, which still leaves me with 3v. And I'm just on the bottom, I'm doing 4 times pi, so 4 pi equals r to the third. And in order to get rid of the exponent of 3, we will need to use the cube root, the third root of both sides. The nice thing about third roots is they can be positive or negative, and that actually is a nice thing for us because we don't have to write plus or minus. when we do that. You only have to worry about plus or minus when you cancel an even power with an even root. So here, it's not an issue. So we get that the radius of a sphere is equal to the cube root of, oh, forgot my 3. 3 times the volume divided by 4 pi. That is an equation for the radius.
Mr. McCutcheon,
Yes, ma'am.
what happens if you were to put a plus or minus in front of the cube square root? Would it change the value of the thing or would it not?
Well, it says radius equals. Can radius be negative?
No.
And there you go. So we can't have a negative radius, so the plus or minus wouldn't make any sense. And if you were to put a plus or minus in front of a cube root, people might look at you crazy because you only need plus or minus when you are canceling even powers. Was that a hand up or stretching? We're done with part B. We're going to do part C and we're going to call it there.
Because I thought you weren't allowed to have a cube root or square root in the denominator for fraction.
Okay, so he wants to know why we're not rationalizing the denominator or something like that. You ready for the answer? Because who cares? Honestly, it's one of those math rules that we teach you as a rule, and then when you learn more, we go, nah, nobody really cares. So actually, radicals in the bottom of fractions, pretty darn common to be honest with you. And when we do the trig later in the year, I'm going to be, most of the time, I'm going to be like, please don't rationalize that denominator. It makes my life harder. And that's why, because professors and stuff like that, they're not trying to figure out if you played with the radicals properly. They want to know, can you do the trig, you know? So usually, yeah, you're supposed to rationalize the denominator, but there's very, very few times where I'm actually going to make you. And I'll warn you, like, hey, for this stuff, we need to rationalize the denominator. And the only reason why is because Miss Klein wants us to, honestly, because we give the same tests. And she's like, no, I want them to rationalize the denominator. I'm like, and I just said to her, I'm like, and I say her name, I'm like, Klein. I say her first name. I'm like, who cares? But she does for some reason. So I'll warn you when you need to. And part C says, write an equation that gives the radius as a fraction of the time. So what we're looking for here is this. It wants r of t. Well, how's that going to happen? There was no time in the volume of a sphere. No, but you know where there was time? In my volume equation that I used. So if I wanted a radius with respect to time function, then what I do is I plug v of t into r of t, or into r, because now that'll generate the letter t in my volume function. Excuse me, my radius function. Sorry, I said the wrong one. So you can plug it in. You get the cube root of, and on top, we have our 3, and on our bottom, we have our 4 pi. But instead of capital V, I'm going to drop in v of t. And this is how we end up with time in our radius function. V of t is 44t. And we can clean that up. We can clean that up a little bit because the 44 over 4 reduces to 11. So we get the cube root of 11t over pi. Wait, I lost my 3. Crud. You know what? It'll be easier for me to just 11 times 3, so 33. 33t over pi. There it is. All I did was plug in v of t into my radius equation, and now there's a variable. And then the last part says, what is the radius after 5 seconds? And you can legitimately just plug a 5 into your radius equation now. So it's like, what is r of 5? And of course, you would grab a calculator, right? Cube root of 33 times 5 divided by pi. And I will save you the trouble, and I'll just tell you it is approximately equal to 3.74. Of course, we're talking millimeters here. And that is where we will call the notes for today. Are there any questions about part C, how we were composing? No? Okay, cool. All righty, we'll pick it up tomorrow.